in terms of the pericyclic reaction. So I want now to look at a different case of a 4+2 cycloaddition, which is actually 4 electrons plus 2 electrons, but it's actually 3 plus 2 in terms of atoms. And this is the 1,3 dipolar cycloaddition. I need to introduce that, say something about what are dipoles and dipolarophiles. Then because it's a very big area, I've chosen some examples in target synthesis. There's a little bit less theory this time, a little bit more showing how the reactions are used. So first of all, I need to show how this kind of reaction fits into the idea of pericyclic reactions. So 1,3 dipolar cycloadditions are very good for generating now 5-membered rings. So that's where 3 atoms plus 2 atoms comes in, rather than the 6-membered rings of a Diels order. So it is still, though, a 4 pi plus 2 pi cycloaddition in terms of electrons. It's 3 plus 2 in terms of atoms. Again, geometrically, we have got suprafacial approaches, just because that's the only sensible way for the two species to approach each other geometrically. We have a 1,3 dipole instead of the diene. It's a 3-atom component. It does have 4 electrons that are going to be involved in the cycloaddition. If I generalize it as A, B, C, the central atom B has a lone pair, a non-bonded pair of electrons to allow a resonance overlap with one end of the dipole. And the central atom is very often nitrogen. So pretty much, I think in almost all the examples I'm going to use, it's nitrogen. But it needs to be an atom with non-bonded pairs. So the central atom can't really be carbon, for example. The 2-atom component, we called it a dienophile, where it's reacting with a diene in the Diels order reaction. Here it's known as a dipolarophile because it's reacting with a dipole. It's a 2-atom component. If I call it D and E, it just needs a pi bond. It could be a triple bond. Well, I didn't mention that with the Diels order, but the dienophile, just as this dipolarophile, could be a triple bond, but we need 1 pi bond to be able to react. So in prototype, it looks like this, where we have a 1,3 dipole, where formally we have a positive charge, an electron-deficient center, and an electron-rich center with a negative charge. And here is the 2 pi component. But really, you're not going to get, as a free species, an electron-deficient atom here. So if it's a carbon, it would be a 6-electron cationic carbon. That's not going to exist unless it is stabilized by delocalization overlap with a lone pair on the center atom. And when you do that is when you see that this is a 4-electron component. So for example, here is one. They behave, do come in please. Formally, this is a carbon-nitrogen-carbon dipole. It works better with a substituent here which can stabilize the formal negative charge, so usually an electron withdrawing substituent, but these Azomethine Ylides behave as a 1,3 dipole, a 3-atom dipole with electron deficiency at one end, electron rich at the other. But as I say, they only really can be thought of because the lone pair, non-bonded pair on the central nitrogen, overlaps with the formal cationic center to such that a more realistic resonance form is this form. But of course, I will normally draw them like this, and it looks, people say, well, why isn't that a 1,2 dipole? Because it reacts like a 1,3 dipole, because electrons attacking this center here push this pi bond back towards the nitrogen. So that's where, so if I was to do that, if I was to have a double bond between A and B here and a plus on B, I would have to have a second arrow. And that's why this is a 4 plus 2 in terms of electrons. There's a 2 on the alkene, and the 4 would be the pi bond in the stabilized resonance form, and the lone pair of electrons that gives you the overall negative charge on the formally negative end. Here is another example. I'll show some more as we go through. This is a carbon-nitrogen-oxygen dipole. Again, I'm only now drawing it in the stabilized resonance form, but again, it behaves as a 1,3 dipole by forming bonds to the carbon and to the oxygen. And that's called a nitrone, and we'll say a bit more about that as we go through. So here are two examples, one of which is showing why, even if we draw them as a 1,2 dipole, they behave really as 1,3 dipoles. And emphasizes the need for a lone pair atom in the middle. You can also have dipole, that was, let's go back one. Notice that this atom here is an sp2 hybridized atom in the center. You can have sp hybridized atoms in the center, where the 1,3 dipolar form already contains at least one double bond, but you can draw a form where here, if I look at that top right-hand resonance structure, which looks like a 1,3 dipole, if that central atom there, I've drawn it, called it XYZ on this slide, but if that central atom has a non-bonded pair able to stabilize the formal positive end, you'd get this kind of resonance form, or there is an alternative where I have a triple bond and a negative charge. But again, both of these forms look like 1,2 dipoles, but they behave like this. They behave like 1,3 dipoles. And here are some examples. Here is, again, I'm only drawing one resonance form this time. I'm drawing this kind of resonance form, which has a triple bond and a single bond. So here would be a nitrile ylide. There seems to be a dispute about whether you spell ylide with an E in between the D and the S or not. So for example here, if you have a chloroimine, which you can form from an amide by treatment with phosphorus oxychloride, for example, and a proton that can be removed on the next door carbon, then you can, those curly arrows lead to this resonance form, and that's a nitrile ylide, and you see you can draw these alternative resonance forms if you wish. But there is a nitrile ylide, and that is a CNC dipole that is actually more oxidized than the azomethine ylide that was on the last slide, which was double bond, single bond, rather than triple bond, single bond. So that's but was also a CNC dipole. Here's a nitrile imine that is a CNN dipole. Here is alkyl azides, which you can form quite easily by doing a nucleophilic substitution reaction on a primary halide with the azide. That's not right, is it? Is that, or that should be, yeah, that should be R dash, because that's now R. So it's substitution here, but that's not the same R then because I've lost a carbon. But by reaction of azide anion with leaving group bearing carbons, so you get an NNN dipole. Nitrous oxide, a gas, is actually an NNO dipole, but doesn't really fit comfortably into this, into organic synthesis considerations. That's alkyl azides. Here, diazoalkanes, which are CNN dipoles. A bit like the nitrile imines, but at a different type of oxidation level. Again, you can get those by taking a hydrazone and oxidizing, for example, or coming right round to a nitrile oxide. This is a more oxidized version of the nitrone that was on the previous slide, where you've got, you could take a hydroxymoyl chloride, so a C-chlorinated oxime, for example, treat it with base, and you get these nitrile oxides. So these are all cases where you can draw a triply bonded resonance form, and you still have a plus minus, but drawing the triply bonded resonance form, it looks like a 1,2 dipole, but reacts as a 1,3 dipole. I think on the next slide I've got some more of the dipoles with an sp2 hybridized central atom. So these are double bond, single bonds, like the two examples I had 2 slides ago, like Azomethine Ylides. Azomethine Imines are similar, but with CNN instead of CNC. Carbonyl Oxides, the name is descriptive, it's an extra oxygen on the end of a carbonyl, so they're COO dipoles. Carbonyl Ylides, I've got some examples of that in synthesis, that's a COC dipole. Ozone, gaseous ozone in ozonolysis. When you learn about ozonolysis in early chemistry classes, but it is a dipolar cycloaddition because one resonance form of ozone is a 1,3 dipole, or behaves like a 1,3 dipole. And then nitrones, so azomethine ylides and nitrones were the ones 2 slides ago as my first introductory examples of dipoles. So there's a fair number of different dipoles. There are more, and you can find those listed in reviews and textbooks, but I think that's enough examples that you can see you can have a certain amount of variation in these. So what can we do with them? Well, I mentioned ozonolysis as being a relatively straightforward example. So here is ozonolysis, or here's the beginning of ozonolysis to form the primary ozonide, where you do a 1,3 dipolar cycloaddition across an alkene. And here now we've got 3 curly arrows. That emphasizes 2 electrons here and 4 involved here. So it is a 4 plus 2 cycloaddition in terms of electrons, 3 plus 2 in terms of atoms. That's a Woodward-Hoffmann type description, so ignore that. This falls apart in the classic Kriege mechanism to give a carbonyl group and a carbonyl oxide, but a carbonyl oxide is a 1,3 dipole. So to form the conventional ozonide that then is isolated, can be worked up to effectively break apart the 2 carbons of the alkene, is another 1,3 dipolar cycloaddition. So we do a 1,3 dipolar cycloaddition, do a cycloreversion, and then do a second 1,3 dipolar cycloaddition in a different orientation. We can start thinking about whether this fits the frontier orbital picture by looking at HOMO and LUMO. So what I've drawn here, forget that's the Woodward-Hoffmann stuff, and I only put that in for completeness, but here's the frontier orbital, HOMO of the alkene, the pi bond. How are we going to draw this? Well, the nearest thing we've got is the allyl anion. That's 3 carbons in a line with 1 pi bond and 1 negative charge. So this is 3 oxygens in a line with a pi bond and a negative charge. So the orbitals will look similar to the allyl anion, and that's the top orbital of the 3 in the allyl system. It looks like this. Again, I'm not differentiating the sizes here, so I'm not looking at contributions and so on. I'm just looking at orbital phases. So if I then if we say the LUMO of ozone is going to be a little bit like the LUMO of the allyl anion, then we can line that up here, and we see that the 2 ends of it have the same phase as each other. The 2 ends of the alkene HOMO have the same phase as each other. So we can set that up to have constructive overlap. So we can see in principle why the dipolar cycloaddition works exactly the same as the Diels order in terms of frontier orbitals. So it's an allowed reaction. And you can do the same thing for the second one here, the HOMO of the carbonyl. We say, well, carbonyl, okay, it's the 2 ends shouldn't be the same size, but it'll be pretty similar to, in style, like the HOMO of the carbonyl group. The LUMO of the Carbonyl Ylide is, what am I doing there? Yep, it's like the LUMO of ozone is like the LUMO of the allyl anion. So that comes down to here again. You can do it the other way round. If you take the LUMO of the carbonyl, which is pi star, and HOMO of the Carbonyl Ylide, which would be like the HOMO of the allyl anion, then again you can set it up to get constructive overlap. So I have to say, in dipolar cycloaddition, in Diels order reactions, we generally took the HOMO of the diene and the LUMO of the dienophile as being the most generally useful. With dipolar cycloadditions, as in this bottom case, you can have HOMO of the 2 pi component and LUMO of the dipole, or LUMO of the 2 pi component and HOMO of the dipole, give the same result. But which one of those has the smaller gap and influences things like the regiochemistry depends very much on the exact atoms in the dipole and the exact substituents. So here it's a little bit less definite that you will always use homodiene, lumodienophile. Here it depends on which dipole you're talking about. The answer about whether it's allowed is exactly the same. So hopefully with that example, well, there's two dipolar cycloadditions here, we can translate the picture for the Diels order reaction and vary it because we only have three atoms in the dipole, and still show that it's going to be allowed. So I want to look at some examples using these Azomethine Ylides where the dipole is going to be a CNC dipole. These are most easy to form when the formal negative end of the dipole is stabilized by an electron withdrawing group. Well, here I've got it on both ends, but at least an electron withdrawing group at one end. Now, only one, I'll say a bit more about other methods of making Azomethine Ylides, but one way of doing it is ring opening, and this is another pericyclic reaction. It's an electrocyclic reaction. We'll say more detail about that in, I think, the next session. But if you use the nitrogen lone pair to put a double bond here, bring this one round, that curly arrow should actually end on the carbon, not in mid-air like that. It should end on this carbon. It's a bit difficult to draw it that small. You will end up with this kind of dipole. Now, this geometry here, this shape of the thing, depends on the orbitals in ring opening the three-membered ring. It's so-called conrotatory, but I'm going to postpone any more discussion of that until we look at the so-called electrocyclic ring opening and closure. but take it from me for the moment that you get a particular geometry here. We don't have to worry too much about that, because all that affects is in the dipolar cycloaddition, I've shown the dipolarifial, in this case, as a triple bond, so you end up with a double bond in the product, but you end up with the top half of this 5-membered ring is coming from the dipole, the bottom half from the dipolarifial. The geometry of this, which is defined by the allowed way of opening the 3-membered ring, which we'll come back to, determines the geometry across here, that the two esters are on opposite sides. But so this idea that you can take an aziridine, which you might have made from an alkene, for example, and ring open it thermally to give a dipole, an azomethine ylide, and then do cycloadditions with it, has been used by people in synthesis. So here's an example of that, to make this molecule here, which is one of a family of neurotransmitter molecules, the kainic acid family. So this is allokainic acid, which is a diastereomer of kainic acid itself, but is a natural product and a neurotransmitter. So it's a relatively straightforward synthesis in that you put together this alkene, that pi bond here is what's going to be the dipolarifial. Here is the azide that was made with an ester substituent, so that when BN is a benzyl group for protection, when you heat that up, okay, it's quite a high temperature, this ring opens to form a little bit of this, but that you can't isolate this. The bit you isolate is the azide. This is formed in the reaction mixture, and is immediately that reacts with the alkene here to close the ring. So you can draw, if you want to, you can draw a curly arrow from here to the alkene, one coming back from the alkene to the left-hand carbon, and then sending this pi bond back onto the nitrogen. So this is an example then of that ring opening to give, in this case, a 6:1 isomer ratio of endo to exo, and that's where this substituent is in relation to these two stereochemistry. But I'm not going to go into that right now. I just want to show you example of a dipolar cycloaddition. To make the natural product, this had to be a Wittig reaction here to extend this by a carbon, and then there had to be an oxidative step here to make a carboxylic acid. And then at the end of it all, the nitrogen was deprotected and the ester was hydrolyzed. But the bit I'm emphasizing here is that quite high temperatures, but that you can form this dipole by ring opening of a 3-membered nitrogen-containing ring. That's not the only way of making azomethine ylides. And here's other common ways. So what I've mentioned so far is that electrocyclic reaction, which is a pericyclic reaction of its own. How else can you make azomethine ylides? Well, I hope you're familiar with taking an aldehyde and reacting it with a primary amine to form an imine. What if it's a secondary amine? You can't form a neutral imine because there aren't enough hydrogens to get lost from that nitrogen. But you can form an imine effectively, but it has a plus charge on the nitrogen, which means deprotonating the next door carbon, which came from one of the groups on the secondary amine, is reasonably easy. Again, you don't isolate these, you make them in situ. So an aldehyde and a secondary amine is a possibility. Taking an imine, and which should have a positive charge there, and deprotonating it will also give you the that should have a positive charge. That's a mistake. I borrowed this slide from someone else, so it's not my fault. you can either deprotonate an iminium salt like this. Actually, that middle R shouldn't be there, and I know what this is. Yeah, that should be an H there. Sorry, that should be nothing there, I beg your pardon. That should be a lone pair there. So you alkylate the nitrogen with an alkyl halide, which gives the quaternary salt plus here, and then it becomes easier to deprotonate it. So I'm sorry, I didn't notice that error until just now. You can also do cycloreversion ring opening here to form the Azomethine Ylides, but the two commonest ways of making them are from aziridines. That requires quite a lot of energy to start, or to get over the energy barrier to break the ring, or aldehydes and secondary amines. Now I think I've got some more examples of, yeah, here we go, of syntheses using Azomethine Ylides. So here is the dipolariphile double bond here, and here is an imine at the other end. So how are we going to make the Azomethine Ylide from this? We're going to deprotonate here and protonate there. So we're going to do a proton transfer effectively from carbon to nitrogen. Now there won't be very much of that happening at any given moment in equilibrium, because that's making a sort of dipolar species from an uncharged species, but enough of the proton shift from this position to that position can happen that and with the dipolariphile in the same molecule, you get intramolecular reaction to form this 5-membered ring. That's been used in a much more complex sequence of steps to put rosiofillin together in a letter in Synhet in 2003. But the bit I want to concentrate on here is taking an imine, that you need something to quaternize the nitrogen. On the previous slide I mentioned perhaps alkylate it with a halide, but here it's a proton shift, so loss of a proton, that's triethylamine as the base, to lose a proton, but the nitrogen picks it up. Small amount of the dipole is formed, and in an intramolecular reaction is captured directly, straight away. Here is from Tom Livinghouse, a bit older, 1996. Here is an imine. This time the nitrogen is going to be alkylated with this trifluoroacetate, trimethylsilyl on a CH2. So the nitrogen lone pair here will substitute away the it's not trifluoroacetate, trifluorosulfonate, I should say. We'll remove this leaving group anyway and put the CH2 trimethylsilyl onto the nitrogen, and then that will be this trimethylsilyl group will be removed by fluoride. Fluoride will attack the silicon of the trimethylsilyl and generate a small amount of CH2 minus at this position. So this isn't deprotonation, this is desilylation. But that will make a small amount of the dipole here, and again it's set up to do an intramolecular reaction with this alkene. So the two ends of the dipole, CNC, will react with the two ends of this alkene to form this single bond and this single bond. So the alkene used to be there, and we form the two single bonds to it. And that's the skeleton of the erythrina alkaloids. And of course, if you build in the right substituents and so on, you can start elaborating that. So those are two examples of different ways that a small concentration of Azomethine Ylide can be made in situ, and then snapped up directly, as long as the dipolariphile is already there, in this case, in both of these cases, in the same molecule, so it can't help but be already there. This one, it's not a fantastic yield, but it does give a single diastereomer of the product with relative stereochemistry as shown. This one a much better yield, but also a single diastereomer of the two asymmetric centers that are created in the cycloaddition. So they show different ways of doing it. This is kind of quaternizing and deprotonating imine, but it's done by proton transfer there. And this is alkylating the imine and then not deprotonating, but desilolating to make the formal negative end of the dipole. So you can see there are various possibilities here, so you have to be aware of that when you're either planning or when you're looking at work some other people have done to try and understand how and why it worked. Shift to a different dipole. This is nitrone cycloadditions. So this is the CNO dipole, one that was on my very first slide, formed between aldehydes and substituted hydroxylamines. So if you take a substitute, it's a bit like forming an azomethine ylide from an aldehyde and secondary amine. Here we don't have enough things to be lost off the nitrogen that we could actually form an uncharged species. So if you follow the mechanism through, just like if you're forming an imine or an oxime, you find in the end that you've got to have this dipolar form. If you then put in an alkene, adds to it, and you form a heterocycle, which is an oxazolidine. I beg your pardon, an isoxazolidine, but it's an NO single bond in a 5-membered ring. But that can be used because the NO bond, in some cases because the NO bond is easily cleaved, and in other cases because you can do different things with it. So here was Bob Stockman from my old university in Nottingham, who was trying to think of a way of making this histrionica toxin, which is one of the toxins found in the skin exudates of certain frogs in South America. And it's been an interesting synthetic target, partly for its biological activity and partly because of its unusual looking structure with this spiro ring junction here. So that's the structure. This is the retrosynthesis that he thought about. Imagine joining that N and O together, and then you've got a 5-membered ring here that looks like that one there. So you could imagine this is a retrosynthesis. You can imagine undoing that to give you a nitrone and a double bond here. If you unwrap that, that's what it looks like. And what you've got to do now is join that nitrogen across that carbon to make this kind of nitrone dipole, and then hope it does the dipolar cycloaddition. So here's how it's put together, a symmetrical molecule, in fact. Both of these are Z double bonds for the N stereochemistry. You make the oxime, looks okay, but you've set this up to have a double bond there that has a withdrawing group on it, so you can effectively do a conjugate addition there to close the ring. But that makes the nitrogen plus, so the oxygen has to become minus to balance it out, and you've made your nitro. You've still got this other double bond left hanging off the other side, and sure enough, its ring closes. This is then an example of, we've reverse of the dipolar cycloaddition, and then reforming, in fact, the opposite regiochemistry. So it first of all falls with the oxygen attaching next to the nitrile, and here now we're going to form the oxygen attaching remote from the nitrile. So effectively we do one dipolar cycloaddition, and this time it's, if you heat it up, you do manage to reverse it. This is quite a strange system, but now the dipolariphile turns over, and so you redo the dipolar cycloaddition, but with the opposite regiochemistry here, which creates the framework of what you want for histrionic toxin here. And obviously this needs to be further modified by reducing the NO bond and modifying the two nitrile groups and chain extending them. And in fact they're both chain extended. If you look, they're chain extended with the same functionality, so you can do the same to both groups. But the reason I've shown this is how you make the nitrile oxide here, sorry, the nitrone, I beg your pardon, here. You do a dipolar cycloaddition. It doesn't go the way you want it to, but if you heat it up, then it flips over to give what must presumably be thermodynamically more stable. Again, you'd need to make a model to prove to yourself why that's the case, but certainly that's what happens. So dipolar cycloaddition, reverse, recycloadd, but with the regiochemistry of the dipolariphile switched over. Sorry, what was the question? I think this one is thermodynamically controlled. So this one will be the kinetic product with the orbital control. I don't have the, I can't tell you what the different coefficients are there, but this is the kinetic product. You can reverse it, or you've got to heat it up. This will, you might say, why doesn't it go back to that one? Because this is this must be the thermodynamically more stable product. So this one is the orbital control one. This one is the stereochemically controlled one. But yeah, you have to find out why it goes this way kinetically. You have to go in and check out the orbital coefficients for that setup. And that gets more complicated because with 1,3 dipoles, it's much more difficult to know exactly what the different orbital contributions could be. In fact, usually most people in those cases have decided what the orbital contributions should be when they've found the product. So they've retrofitted the answer. Because it's much more difficult to do the calculations. It's not so easy to do the kind of approximations that I showed with the Diels-Alder diene cases and so on. Yeah, so this is an example of dipolar cycloaddition, reverse dipolar cycloaddition, and then dipolar cycloaddition with different regiochemistry because of different product stability. So if you like, these at 180 degrees, these are all in equilibrium, but it ends up here as the most stable product. In the original planning, it was hoped that this would go directly to this. But of course you don't heat at 180 degrees unless you have to, because your compound will necessarily survive. So they heated it until they found a cycloadduct, but then found it wasn't the one they wanted. And then they then had to see if they could get it to reverse and and do a second cycloaddition. So it was taking a bit of a chance at that stage. In fact, I don't know what the yield for that sequence is. I could look it up, but I omitted to this time. Okay, so that's an example of using nitrones and ending up with, so that's another example also of kinetic versus thermodynamic products, controls of reaction. Or actually, that I didn't make a point here, but nitrones, depending on all the various substituents, you can have either homonitrone LUMO dipolariphile as the lowest energy gap that controls it, or you can have LUMO-nitrone homodipolariphile as the controlling one, because it depends on the substituents on the dipolariphile, which I said, but I hadn't actually pointed out that it was already on the slide. With the azomethine ylides, it's much more common for it to be homodipole LUMO-dipolariphile. With nitrones, the energy levels are such that even with the sort of prototype no substituent one, the two energy gaps are not very different. And that does make it hard to predict, because you don't know what your particular one, your complex one, is going to be like until you've made it and tried it. So if we go to a slightly more oxidized one, so that would, if you wrote it in the sort of dipole, 1,2 dipole form, the nitrone had double bond, single bond, with double bond CN, single bond to oxygen. Nitrile oxides are triple bond CN, single bond to oxygen in that particular resonance form. And two main preparation methods here. One is going from the sort of imine type compound. You can take an oxime and actually you can C-chlorinate it if you use N-chlorosuccinimide, or actually some bleach or some chlorine. Any of those methods, that's not all in one pot. Those are alternatives. Anything that will give you a positive chloride, effectively a Cl plus source, you can chlorinate on carbon, and then that eliminates in base to lose a proton and to lose H plus and Cl minus, and that gives this nitrile oxide species. A less obvious method until you've seen it, and I'm not going to do this now, but you practice this for yourself on pieces of paper. If you take a primary nitro compound, treat it with an isocyanate and any sort of dehydrating reagent, this is DCC, dicyclohexyl carbodiimide, that people use to do peptide bond formation, but it's the same compound. If you work that through, again, you can dehydrate an alpha nitro compound. And if you look at it, two protons have come from the CH2 next door to the nitro, and one oxygen. So we have overall lost water. But that's quite a fun practice of curly arrows to go through that one. So there are nitrile oxides. What can you do with those? Now, I've included them because they have been used in synthesis. So here are a couple of examples. Kozikowski was one of the early guys to work here. So he constructed this indole derivative. That's going to be the dipolariphile. Here's the primary nitro compound that's going to be the source of the nitrile oxide. So if you use the Mukayama method, actually I was slightly wrong on the last slide. Yeah, you need isocyanate or DCC. It's alternatives like that, I beg your pardon. Using either phenyl isocyanate or DCC in catalytic base. The slide's not very clear on that, I apologize. So those are alternative dehydrating reagents, like these are all alternative chlorinating sources. But in both cases you need catalytic base for the dehydrations. That's why there is just the isocyanate and triethylamine, TEA, triethylamine here. You are forming in situ the nitrile oxide. So there's your dipole, 1,3 dipole, ready to react with this dipolariphile, and that's what it does. The nitrones formed 5-membered NO heterocycles with no double bonds in. Here, because we've got one more double bond in the dipole, we end up with one double bond in the 5-membered NO ring. So this is an isoxazolene, that ring, whereas the one with no double bonds in is an isoxazolidine. But the names don't matter too much, it's just that obviously if you get the structures right. So that's put that together. The key here is it's formed that CC bond and that CO bond. But we don't actually want this ring, so all that's is done now is this NO bond is cleaved reductively. The CC bond is kept because that's the critical one to be made, and then modifications are made to this side chain from this 2-carbon piece here. It's been extended a bit, and the nitrogen's been modified. But the key for that was to use the dipolar cycloaddition to make that CC bond. The stereochemistry has also been set appropriately. A slightly more recent one is here, just to make an analogue of a medicinal natural product, mitomycin. So here's been set up on a benzene ring with an oxime this time, and the double bond here is going to be the dipolariphile. So we're going to take an oxime, we need a positive chlorinating reagent. So bleach is used here, sodium hypochlorite. Actually this will be a 2-phase system, so it'll be bleach in water with dichloromethane. This happens at 0 degrees. So you C-chlorinate, and then you eliminate H plus from the oxygen, Cl minus from the CCl bond here to form, again, a nitrile oxide, so it'll look like that, that's stuck on here. And then that adds across this dipolariphile double bond to form this 5-membered ring, and we've made top and bottom bonds of the 5-membered ring there. Again, the key here has been to make this CC bond. And then a lot of modifications, and that was taken through to this target biologically active molecule. Again, the NO bond isn't wanted, you can reductively cleave that, and then you can start modifying all the other substituents. So I'm focusing very much on the dipolar cycloaddition part here, that in this case is making critical CC bonds. And in both of these cases, the NO bond has been sacrificed because you don't need it. It's there to help guide everything else, because it comes with your dipole. Here's an example of Carbonyl Ylides, Ylides, in the synthesis of Illudin M, which is down here, bottom left. This is a different way of making Ylides, and as I said at the beginning, in this lecture I'm picking out a selection of all the possibilities. You could do a whole week just on how to make 1,3 dipoles, in fact. So here we're taking a diazo ketone. We're treating it with rhodium, which will abstract that nitrogen and make a rhodium carbene complex. So think of this carbon here attached to the rhodiums. Actually, if you think of it just in organic terms, it's a carbene. More about carbenes tomorrow afternoon, or maybe Wednesday morning, I forget. But anyway, the carbene attaches or interacts with one of the oxygen lone pairs, and what you end up with is a carbonyl ylide. And if you look at that, it's a COC dipole. The formal plus is on the oxygen, so this top end is the sort of more positive end of the dipole. This bottom end, that's a negative there, it's come out rather small in the slide, as the sort of formally negative end of the dipole. And you can add that, this is all happening in in the same pot, present is this molecule in blue, which is going to be the dipolariphile, this alkene. And you can see it's, I've coloured it so you can see where it is. The two sort of orangey red type bonds are the ones that have been made in the dipolar cycloaddition. Now you don't really want this oxygen bridge in there and so on. So that's broken down. If you imagine taking a proton off this position next to carbonyl, then you can form a double bond here and expel this oxygen so it becomes a substituent. But the critical thing is you've made these two C-C bonds at the same time as each other. And then more modifications take you through to the Ylides natural product. So that's a carbonyl ylide made from a carbene onto heteroatom joining together to give you an ylide that way. Now the last bit I want to go through has various bits of chemistry within it. This is GIAN's nominine synthesis. This is the thing he was trying to make. These are the disconnect. I'm going to do the retrosynthesis first. This is the sort of, he was imagining putting together all those bonds with the red lines through them. So this was his thought process. This side, so these two on the right here, that's a Diels-Alder reaction. So that's applicable to what we were talking about before lunch. This side is a dipolar cycloaddition. So here is an azomethine ylide, and here is an alkene waiting to add to it. So that would be appropriate to these two bonds. So how are we going to get to something like this to be able to do that? Well, now where do I start? What's the best way to describe this? Well, let's think about what that is in terms of the 1,3 dipole. How are you going to help to stabilize that? And what was done here was to make this sort of isoquinoline structure, but with a substituent on the nitrogens that is positively charged. Then if you've got this oxygen here, that will deprotonate to form a neutral, or sorry, not neutral, an overall uncharged, neutral, a plus-minus species. And that doesn't look like a 1,3 dipole until you draw a different resonance form of it. So until you think of this oxygen in a carbonyl form, then, so push these electrons from the oxygen up to the top here, then if you could make something like this, it should behave like a 1,3 dipole. So it would be good if you could have this oxygen substituent in here to help you towards this 1,3 dipole. If you could do it, this is the dipolar cycloaddition he was thinking about. But it doesn't, and then you might be able to imagine a bit here that you could elaborate to that bit there, and so on and so forth. But just concentrate on the 1,3 dipole bit. Here's how you might put it together. Here's how you might take this and what you might do with it in terms of a cycloaddition. So we should perhaps look at what he actually did. So he took this structure, converted this ketone, reduced and chlorinated, took that, got rid of that altogether by a radical reduction. Well, don't worry too much about what's happening there. Modified this cyano group by reduction to an aldehyde by dibal and hydrolysis, and then doing a Wittig reaction. And then didn't really want this whole benzene ring, because he wants to be able to do the Diels-Alder with it, so you don't want it aromatic. So he reduced it in a Birch type reduction to give this cyclohexadiene type system. Well, this function here is a hidden ketone. It's an enol ether, so you can hydrolyze it. So he's now got something that is kind of ready to go on the Diels-Alder reaction. So how are we going to do that? This is the diene at the moment. You make an enamine from this carbonyl. Now, if you do that straight away, the double bonds are not going to be in the right place. But if you give that time for the double bonds to come into the appropriate conjugation, only when you've got this arrangement of the double bonds will it be set up to do the right Diels-Alder reaction you want to do. So that's the first pericyclic reaction. It's pretty complex, so I wouldn't expect any of you or me to predict this, but that's how it was all set up to do the Diels-Alder part. What's happened there? Have I lost one? Oh, okay, right. I engaged myself. I've gone back one now because yeah, that's better. Okay, so yeah, did this all in the wrong order. Got myself confused yet again. Okay, so right, set up this structure so that it is a dipole, and then this is that drawn differently. That's better. And does the dipolar cycloaddition. So here's the first cycloaddition, and then if you that's it. That's what I couldn't get. If you redraw that, it's like this, which is on the next page to get ready for the Diels-Alder. So I should say that again just to make sure I've got it correct. Sets up this molecule, which is a dipole in disguise. Does the dipolar cycloaddition. Redraw the molecule. It looks like that. And here's just an example of the different isomers you could get depending on which way you have the dipole, because there's a twist around these bonds here. So there are two possibilities, and that's these two here, depending on which orientation or which regiochemistry the dipolar cycloaddition does. And I think it's that's right, it's the top one here was the one that's taken on further, yeah, okay. So let's just stop at this, with this one and go back over it again. Construct this, I've not gone back to the synthesis of that, which you might draw like this, because you might have made it from a hydroxy isoquinoline by an alkylation reaction, but as soon as you do that, it is actually a masked dipole. And if you wrap that, it's not so easy to see from that, this alkene is reacting with this dipole, and then it depends which end of the alkene attacks which end of the dipole. You get two possibilities here to give you the complexity of system that you want to take forward. And in fact, it was that one that he then used to set up to do the Diels-Alder reaction, which is this part of the retrosynthesis. Okay, so I didn't explain that all that well, but because I got it back to front slightly. But so a dipolar cycloaddition, which is going to be followed by a Diels-Alder cycloaddition. So make a dipole, do the cycloaddition. You don't get complete control of regiochemistry, but you get some of what you want to go forwards. And then this is modified by getting rid of the carbon, changing the nitrile and so on, reducing the benzene ring to do the Diels-Alder. But this bit is the dipolar cycloaddition, and it illustrates that you can twist around the CN bonds to get both regiochemistries. Okay, so that's a very much more complex example. So what I think has happened in this session is we've seen applications of 1,3 dipoles, less concentration on the orbitals and so on, just enough to know it works, partly because the way I answered the question I had earlier, it's very much more difficult to predict the exact regiochemistry and so on. This is, I suppose, an example of it in dipolar case, because the effects with having all the heteroatoms and different substituents, it's a much less clear picture than it is with the Diels-Alder reaction. But nevertheless, you can find many examples of dipolar cycloadditions, and you can use them in many cases in natural product synthesis. So that's the end of that session. Took a little bit longer at the end because I got myself confused on that last example. But thank you very much. We take a break now, and then we're back again, ideally at 3:30, but it'll probably be about 3:40, I would imagine. Okay?
So may we have a 10-minute break, and so that the second that we